Bet you didn't know that when Santa was a young man, he had to take a statistics course. When the class started covering two-sided hypothesis tests, he had a lot of trouble remembering where to put the equal sign. He started repeating to himself, the equal sign goes in the null hypothesis. The equal sign goes in the null hypothesis. The equal sign goes in the null hypothesis. Eventually, he shortened this phrase to make it easier to remember. In fact, to this day, you can still hear him say, ho, ho, ho. Get it? Null hypothesis. And we are going to still be using null hypothesis today as we learn how to use the Chi Square test for goodness of fit, or the GOF test. So we're going to go ahead and take a look at an example in AP enrollment. So as teachers, we try to make sure that all of our students succeed, regardless of race or ethnicity. We frequently examine statistics to see how well we are serving our different populations. Now, the demographics for Cedar Ridge in 2019 are listed here. African American was 13.2%, Hispanic 38%, other 4.5%, Asian 6.6%, and white 37.6%. Now, in 2019, we had 925 students enrolled in AP courses, and we're going to assume that this group that we're going to look at is representative of Cedar Ridge students over time. Now we're going to test the results using a chi-squared goodness of fit test. So you'll be happy to know that the structure is very similar to what we've done before. We start with a state where we write our null and our alternate hypothesis. So what are we checking? We're checking to see if our sample is reasonably close to our model. So we can write a null hypothesis for our sample of AP students that the proportion of ethnicities among AP students matches the proportion of ethnicities for the entire student population. Now, let me go back very quickly and say I could say the P1 for African American equals 3.2, P2 equals 38, P3 equals 4.5, P4 equals 6.6, and P5 equals 37.6. So I could write it that way. Usually on these, though, it's a lot easier to write it in words, and that's fine, okay? Now, the alternate hypothesis is that at least two of the proportions will differ from the model, all right? And that's pretty much how we can say it. At least two of the proportions is different from the model. And why two? Well, if one of the proportions is off and it has to add up to 100%, that means two of the proportions are off at a minimum, okay? So expected values are something that we're going to calculate, and that's basically what we would expect to see from the model. So we take the proportion of the sample size for each category designated by the proposed distribution. So decimal values are fine for expected counts. So we have 925 AP students. We would take that, since they're 13.2% of our population is African American, we would multiply that out, and we would expect to see 122.3 African American students in AP Stats. Now you're going, 122.3, shouldn't it be 122? Expected counts, it's fine. It's just like averages. It's understood to be a statistic, so don't worry about that one. Asian, if we apply the same proportions, we would expect to see 61.5 Asian students, 351.5 Hispanic students, 347.8 white students, and 41.6 other. All right? And that can be like two or more races and other categories. Okay, so now that we have our expected counts, right, are the different ethnicities properly represented in AP courses? So here are the actual counts of African Americans, Asians, Hispanics, white, and other. All right, so you can see, and in fact, you could just a very quick look, you can see that African American is low, Asian is actually high, Hispanic's a little low, and white is a little high, and other is a little low. Okay, so the observed values for African Americans and Hispanics seems low, and the values for Asians and whites are higher than expected. All right, so goodness of fit GOF determines whether a distribution of counts in one categorical variable matches our model, like we said before. So we're going to look at the difference, all right, observed minus expected, also known as a deviation. So what I did is I went ahead and subtracted 79 minus 122.3, and I get a negative. So I do want a negative when my value is lower than expected, and I want a positive when it's higher than expected. So based on this column, which groups are overrepresented? Looks like the whites are the most overrepresented, followed by the Asians, right? Because those are the highest counts. And which ones are underrepresented? It looks like Hispanic is the most underrepresented, followed by African American. Okay, so that's based on the counts. But can you think of a disadvantage of just using this? Well, the thing is, maybe we might be underestimating the impact of Asians relative to size because we expected 61.5, but we have almost twice as much really here. Whereas this 43.3, it's not quite as big, you know, it's not even 100% of that expected, whereas this is almost a whole other expected. So what could we do? Well, why don't we look at the proportions? So we're going to take this value and divide it by the expected. The proportions here, which groups are underrepresented, you can actually see that African Americans are the most negative here, but it's really tied with this other group, and then Hispanics not so much. So African American and other students are now the most underrepresented based on this statistic, and most overrepresented would be Asian students, all right? So can you think of a disadvantage to using just this number? Well, I'm suspecting that it's kind of overestimating the impact of other, right? It's giving a higher emphasis to small changes in small groups. So how can we compromise? We can go ahead and treat this as a weighting factor and then multiply these two numbers out. And you come up with, so it's like, here's the difference and here's the weight based on that difference. So if I go this times this, I get 15.3. And you'll notice that all the products are positive now. So that's a common effect when we go ahead. And in fact, if you look, here's why. I'm doing observed minus expected squared. And I'm dividing by expected values, which are always going to be positive. So these numbers right here will always be positive. And you can see that the least contribution is actually from the other. But if I was looking at it here, I would think it was a player in the differences in the model. So now we see the biggest contribution is clearly from the Asian students, why we don't seem to be fitting the model. Now, again, you still do see some impact on African American, Hispanic, and white, okay? So this is called the Chi Square Test statistic, which is basically your observed minus your expected squared divided by expected, and you sum it for all of your categories. So if we were calculating this, basically this is that column that we saw, 79 minus 122.3 squared over 122.3. And you would do that for the entire set of categories, all right? And when we added them up, in this case, we get 89.2. So this is our chi-square test statistic. How are we going to use that? Well, we're going to use, it's basically used for categorical data, all right? So don't think that this is like sample size. So there are different curves for different degrees of freedom. But instead of degrees of freedom being sample size minus 1, I had 925 students. It's the number of categories minus 1. So in our case, we have 5 categories, so our degrees of freedom is 4. What does this distribution look like? It really changes a lot based on your degrees of freedom. So if you have only 1 degree of freedom, it looks a lot like that, sort of like an exponential. And then it starts getting a peak after you get to 3 degrees of freedom, and there you can see 5 and 10. So basically, curves with lower degrees of freedom are more strongly skewed to the right. As the degrees of freedom increases, skewedness to the right decreases. So it starts to look more symmetric. So you can see on this degrees of freedom of 10, that's what the curve looks like. Unlike the normal and students distributions, the chi-squared distribution only does right-tail tests. So we're only looking at how extreme our value is and to the right. So that's the nice part. You don't have to do two-sided. You don't have to do left-sided. We are only doing right-tail tests. Now, the mean of a particular distribution is equal to its degrees of freedom. So if I have, let's say, degrees of freedom 3, the mean is actually at 3. If I have degrees of freedom of 10, the mean is actually at 10. Now the peak's not at the mean. The peak is just 2 over. So if you have 10 degrees of freedom, it peaks right about 8. 5 degrees of freedom peaks right about 3. So that's a cool fact. Not necessarily something you'll get tested over, but it does give you a good feel if a chi-squared statistic is close to the mean, then it's probably not that unusual. But if it's really high above the mean, then it would be. So if we have 4 degrees of freedom, we know that the average chi-squared statistic, if it's just typical stuff, would be about 4. All right. Obviously, ours is much higher than that. So we still have to do conditions, and you still have to, this is part of the plan section, and our procedure would be the chi-squared goodness of fit test, or the GOF test. So for conditions, we either use random sampling or random assignment, right? Note that if the sample is representative, this also meets the condition. If you're sampling without replacement, then you also need to do the 10% condition. Remember, this is not required for experiments. Large counts means all expected counts, not observed. You can have 0 observed counts, but all expected counts are greater than or equal to 5. If you have percentages, you need to go ahead and apply those to get your expected counts. If you have percentages for the observations, you need to change those 2 counts. All right, so everything, both expected and observed, must be counts. And here's the other thing: observed counts must be integers, but expected counts don't. So you remember when I showed you, it was like 122.3 and something else, 0.5. There we go. Yeah, we have 122.3, 61.5. That's all fine. These are not integers, and they're both counts. All right. So checking the random condition, first of all, I did say that we're going to say our data is representative in general. So we're not going to worry about it not being random. 10%, we're going to say 925 is less than 10% of students enrolled in AP since we started collecting data. So we're looking historically, not just 1 year. Large counts, all of these are clearly greater than 5. Right? It only has to be greater than or equal to. They're all greater than 5. Our smallest expected count is 41.6. So when you're doing this condition, you really should specify at least the smallest expected counts. They really expect you to calculate your expected counts. So what do we do on the do part? Well, you show the calculation of the chi-squared test statistic using the formula. So yeah, they actually expect you to write this thing out. So go ahead and write it out. Now, if you have like 10 terms instead of 5 terms, you can put a ... just to show that you know what you're doing, but show the beginning and the end. All right. Then, so in our case, our chi-squared test statistic is 89.2. Then we're going to use this to calculate the p-value, which we can do on our calculators using the second distribution. Just like you do normal CDF, you should have seen chi-squared CDF. It's going to prompt you for a lower value, which is our test statistic, a higher value, which is infinity. Now you can go 1 EE99, or you can just use a really large number. That's fine. And then the degrees of freedom. In this case, our degrees of freedom was 4 because we have 5 categories. And believe it or not, our number is incredibly small. It is effectively 0. Okay, now on the calculator, you can put in lists of data. So first of all, you have to make sure you set up your list of observed and expected counts, all right? Then you're going to press Stat and scroll to Test. Scroll to Chi-Squared GOF Test. Notice how it says GOF, goodness of fit, and press Enter. Select the list with your observed counts, normally that's L1, and then select your list with your expected counts, typically L2. For degrees of freedom, enter the degrees of freedom, which is your number of categories minus 1. Now, if you would like to see the chi-square distribution, you can actually hit Draw and it'll shade it in, but most of the time you're going to hit Calculate. And then it shows the output screen. Now, this is for a different set of data, but it's really similar to our chi-squared statistic. And it's 38.56. The p-value is right here. and there's your degrees of freedom. So the last part on a chi-squared goodness of fit test is conclude, just like we were doing on our other hypothesis test. So are you changing your mind about the assumption H naught? So this hasn't changed at all. If the p-value is lower than the alpha, then we're saying our sample is unusual based on our assumptions. It could be your experiment as well. And you change your mind. You reject the null. If it's higher, that's not that unusual. You don't change your mind. You fail to reject the null. Now, you can actually say you reject the null hypothesis. You fail to reject the null hypothesis. All right, that's usually fine. Now, if you fail to reject, that's because you have insufficient evidence for the alternate. Now, alternates normally should be written in context, okay? If you did reject H naught, that means you must have had convincing evidence or strong evidence or sufficient evidence for the alternate. Then finally, there is one little extra piece. On a chi-squared test, because we have these different components and contributions, it's not like we're just looking at one proportion anymore. We like to say which ones had the biggest contribution, all right, the largest. So looking at our example, I went ahead and pasted the table down here so we could look at the individual contributions. And you can actually look at those on your calculator as well. First of all, we know the p-value is incredibly low. It's practically 0 and much less than an alpha of 0.05. So we reject the null hypothesis. There is very strong evidence that at least two of the proportions are different than the distribution of ethnicities in the student body. So two of the proportions among our AP students are different. So I probably could add a little more context there. Now, who was the biggest contributor? By far, it is the Asian students. The fact that we have almost twice as many Asian students as expected. And even though it is a small group, it's not inconsequential here. Maybe if this was a smaller group, it wouldn't be as big a deal. But we have a lot of Asian students. Now, we also have decent contributions. It looks like we have more than average white students, but we also have a significantly less African American. So if you were looking at this, we clearly need to work on enrolling, hint, hint, we need more African Americans, we need more Hispanics, and we could use some more others too. So get the word out to these kids, let them know they should be taking AP classes so that we have our AP students are representative of our entire student body.